And thanks for being so patient. But boy, do we have a fun class for you today. We get to talk about serious counting. Before we jump into that though, there are a couple quick announcements. The most important announcement is that problem set 1 goes out today. It's got 12 problems, and there's actually, 11 problems, and there's an extra credit problem if you want. And we use this thing called the problem set app. And it's something that I developed after teaching CS109 for a really long time. I noticed this point of students would work on problems and you'd like to get the immediate feedback, am I getting this right? So we built the problem set app. You can see the problem, you can write up your explanation, but you can also put in your answer and check, did I get the right number? Now, at the end of the day, we really care that you understand the mathematics. So we really want you to give your explanation of how you got that right number. But you can get that sort of validation that whatever I did led me to the answer that was what the TAs expected. And so you can have an idea if you're on the right track. So the problem set app, it's a gift from us to you. Use it, have a good time. We did build it ourselves, and it does allow for some other cool things. One of the things that it allows for is you can do simulations. Like we can use probability to build things, and I can have you code up things that can solve problems, and you can run it and test it all in this environment. It is a good time. It allows us to ask more interesting questions. Now, this does mean that some of your answers will require some Python. If you've programmed in Python before, fantastic. If you've never programmed in Python before, not a problem as long as you programmed in a different programming language. You can also come learn about Python. We have 2 different Python review sessions, not 1, not 2, both optional. They're both going to be on Fridays this week and next week. They'll be at 5 p.m., they'll be online, and they'll be recorded with one of our fantastic TAs. So come learn about Python, particularly for probability. The first week will be mostly just the semantics of Python, and the next week will be a lot about Python, particularly for this topic. Now, have you ever seen a textbook and they have beautifully written math? Or you look at a handout or maybe an academic paper, and there's really beautiful symbols and, in their textbook? It turns out there's a language for how you could write mathematics to generate these symbols. And it's a language that you'll all become fluent in CS109. It'll be useful if you go into research or if you just want to go make beautiful PDFs that have some mathematics. This language is called LaTeX, and it's pretty straightforward. It looks scary the first time you use it. You write things like /sum. If you want that big sum figure. You use the underscore to say, I want this in the subscript. You use the power symbol to say, I want this in the superscript. And then what comes after shows up on the right side of the sum. But it's a pretty simple language. It's not like Python, where you'll be learning a whole new way of communicating complicated ideas. This is just more of a markup for mathematics. There's a handout on the website that tells you and gives you lots of examples for LaTeX. You don't have to use it for CS109. You can write all your answers without LaTeX and that'll be just fine. But if you want to learn, you absolutely could, and that'd be encouraged because it'll make your problem set look more beautiful. Do we grade you on beauty? No. But does it feel good? Yeah, it's like, oh, look at that sum symbol. Mwah, beautiful. Anyways, LaTeX, there you go. One of the great parts of this class, as you know, are sections. You shouldn't have signed up for a section yet. Because section signups will be going out tomorrow and they'll be open until Saturday. It's not first come, first serve, so don't be like waiting up till midnight to try and like book a spot in your favorite section. Instead, you'll just give us all your preferences, and then on Sunday we'll do a big matching between sections and section times. I did want to give you guys a sense of, hey, what's our expectations when you do your problem set for how much of an explanation you should give? And here's the broad level. You should give enough explanation that you could teach another student in 109 who's just about to start the problem set how to do it with your explanation. So definitely don't leave your explanation blank. That will not give you full credit. Don't just write one sentence, but write maybe a couple sentences to show somebody the idea that you used to get to your answer. And it should be in that level of detail. Something that if we took your explanation and put a little section in a textbook, that explanation should fit into something like a course reader for CS109. Does that sound good? Okay, so explain your work. If you do a reasonable job, we are not going to be overly intense about it. Just do the explanation, and I think we will all be good on that front. Honor code, we have to talk about it, and you guys probably want to understand what the honor code means for CS109. Honestly, if you feel like you are not cheating the system, you're probably doing it right. But there are explicit rules that we list on the website. And maybe one of the things that is pretty obvious is like, don't look for the answer from past quarters. Don't ask somebody in a different part of the world to do the problem set for you. And don't give the answers to somebody else in the class. But maybe you do want to make friends in this class. You do want to work on problems together. We absolutely encourage this. We would love for you guys to make friends and work on these things together. Where do we draw the line? Well, you can work on the problems, you can talk about the problems, but you all have to write up your own solutions. So everybody writes up their own solutions, and that's where we'd like to draw the line for the honor code. If you have any questions, ask us or the TAs. Okay, late policy. You know what? I want you guys to learn this. I want you to all walk out of this class having mastered this material. If you feel like that would be better achieved if you take a small break at some point in the quarter, absolutely fine with me. I want you to get there by the end of the quarter. So I came up with a late period that gives you as much, late policy that gives you as much power as possible. So here's how it works. There will be a due date for problem sets because TAs are students too. We need to grade. We need to be able to give you guys feedback. So there has to be a due date for problem sets. That due date for problem sets, though, let's say you just miss it by 5 minutes. We don't give you a 0 on the problem set. So instead, what we do is we give everybody a free grace period. In fact, instead of 5 minutes, we say, OK, up to 24 hours after that due date, if you submit it, we will take it. And you can use that for things like, oh, I just needed to sleep in a little bit longer, or I just missed the deadline. Now, that's a very harsh cutoff after 24 hours. There will be a computer-moderated moment when it's no longer in the grace period. Now, if you miss the grace period, do we give you a 0? No. We're going to allow you to give yourself long extensions in CS109. And a long extension is about 2 class periods. If you take a long extension, not a problem for us. We'll still be able to grade your assignments on time. The thing is, it could be a problem for you because 109 is a fast-paced class. Like, while you're taking that extension, we're moving on with material, and then the next problem set's going to come so fast. We know how hard time management is at Stanford. Or if you're new to Stanford, hey, quarter system's a crazy beast. So you can give yourself this extension, but we want you to be thoughtful about how you're going to catch up. And you can do this 2 times in the quarter, and you don't really need our permission. We just want you to log your plan for catching up. And if you need it more than 2 times in the quarter, you just let us know. If you need an extension longer than this, there is a small logistic problem, which is we will have already released the solutions, and we'll already have started grading. Generally, we don't take extensions past this 120-hour mark, or what we call the super late extension. And if you need one, if you're in that situation, talk to us as soon as possible, and we'll talk to like academic directors, and we'll come up with like a bigger plan to get you back on track for CS1. It's not like if you miss this, you're out of the class. But we do need to have a more serious conversation if you can't make that very late extension. So basically, I give you all the power to control your life in CS109. OK. This problem set app, man, made with love for you guys. But it's pretty new. I've used it in only 1 quarter before this. We made it last winter. We think it's very robust. It's gone through a whole course. But you might see something that is surprising. If you guys find any bugs, I would really appreciate to know, and I'll fix it as soon as humanly possible. And I'll appreciate you guys letting me know, because we'd like to make a beautiful tool for future CS109 to use as well. OK. Oh, and then some of you have this desire to hack things. I think we're pretty hack-proof. But I would just lightly say, what if we try to hack it after the quarter? Because then it doesn't look like academic dishonesty. So if you want to try and figure out ways that you can poke around and break the problem set app, that'd be fantastic. But let's wait until final exam is done. OK, and then I put one problem on the problem set, which requires a bit of creativity to solve. So it'll be the very it'll be the very last. The very last problem on the first problem set. It's there's an extra credit problem. Sorry, my internet's not very good in Huang. Which is not that important. There's an extra credit problem. You don't have to do it. But if you want to just challenge yourself and try and do something creative and interesting, have at it. There's a cool problem for you. Wow, that's a lot of logistics. I guess we're still at the beginning of the quarter, and there's a lot of things to talk about. Any questions about this before I move on? Yeah? For the extra credit, do you only get credit if it's correct, or is it for the right? Oh, yeah. For that one, I want you to get the right answer. But that's a good question. Generally, actually, that's a great question because it applies to everything else. Like in CS109, if you don't get the correct answer, we generally give you partial credit. Whether it's a problem set, midterm, or final, we generally give you partial credit. But for this extra credit one, I really want to see people get the right answer. In fact, because the right answer is very obvious, it's how you get to the right answer that's more interesting. Good question. Okay. Yeah.
Can you quickly explain? Because I read through the syllabus and it wasn't very clear. Like, what? So what is the problem sets each week? How do we submit them? Like, if we hit check answer, does that mean it's like submitted or what?
Oh my gosh, such a good question. The problem set app is continuously submitting. Like when you're programming, it's on our server. There's no point hitting submit, we already have it. And so it will just stay open until like at one moment the deadline will pass and then you won't be able to edit anymore. So as long as you're editing, we're getting it.
So what's the little submit button?
Oh, it's just placebo. Yeah, click it, and I think it says a message like, this didn't actually submit it because you're constantly submitting. So very good question. Yeah, and when you hit check answer, yes, everything does get automatically put on our database. So if you hit check answer, we know that you've got that green check mark too. Okay, and then there is one last thing for today. If you go to CS109, and you go to lecture 2, oh man, my internet is really slow. Are you guys finding internet slow too? Yeah. Oh, well. Anyways, there is a way that you can go follow along with the questions for lecture 2. But one of the questions for lecture 2 is just, the first question just says presence. And it says, what is the word written on the board? And the answer is purple zebra. You can put this into the problem set app anytime between now and 5 o'clock, and I'll know you are in lecture. And the idea here is, I have thought about this, and I know that coming to lecture is such a good thing for you. It's a good thing for you, it's a good thing for the class. Like, trying to stay on top of a fast-paced Stanford class without going to the synchronous lectures is a very hard task. I've been a student, and I failed at doing that at one point in my career. I've seen lots of people try, and some are successful, but by and large, I know that coming to lecture is a good thing for you. It's also a good thing for your friends. Like, coming here and having a community of learning, what a beautiful thing. So you don't have to come to lecture, it's optional. You get 100% in the class if you don't. But if you do come to lecture, and you fill in the word on the board every single class, or for most of them, so like for 90% of the classes, I'll take 5% off your final exam, and I'll just give you full credit for that. And so it's just a way to incentivize you to come to lecture, but an optional one. Don't take it, is not a problem. If you feel like you can do the final exam without coming to any lectures, not a problem at all. Does that sound cool? Trying something out that's new. If you guys have questions about it, please do let me know. No, most days. Most days? Yeah, I find that about 90%. 90%? Yeah. Like, you don't have to tell me if you're using this. I'll just calculate your grade at the end of the day, and I'll say, is your grade better because you just like rocked the final, or is your grade better because you came to many lectures? And I'll choose whichever one's the max, and I'll give you guys the max of those 2 grades. That was a fantastic question. More questions? Okay. Yeah.
If I type something into... Oh, never mind.
Okay, good times. Oh, the problem set, you can find it from the course website. So if you go to the course website, you can find it. You don't have to do this now. If you don't have a computer, that's not a problem. I'll just have a sheet at the end of the day. You can come in, or at the end of class, and you can come write down your name. So if you don't have a computer, that's actually a great thing as well. Okay. Exciting, but not as exciting as counting. So CS109, we're going to build this beautiful edifice of knowledge, and it all starts with the very humble beginnings of counting. And in last class, we learned about the 2 most fundamental rules of counting, from which all the theories of counting are derived, and from which the theory of probability finds its origins. We learned about counting with steps. You want to count the number of outcomes to a particular experiment? Well, if you break it up into different steps, if it happens to be the case that the number of outcomes from one step doesn't change how many outcomes there are to future steps, you can just multiply the number of outcomes in each steps together to get the total number of outcomes in the experiment. You can take a big counting problem and you can break it into smaller ones if you can find steps that could construct outcomes of the type you're looking at. That's one core idea in counting. And the other core idea of counting is, if we're trying to count number of outcomes to experiment, if we can think of those number of outcomes and we can split it into outcomes either come from group A or they come from group B, we can use this OR method of counting, in which case you say, let's count how many outcomes are from group A, Let's count how many outcomes are from group B. Let's add those together. And then let's subtract off how many outcomes are in both groups. Because it's possible for some outcomes to be in both groups. And if you didn't subtract this out, you would be double counting. And that's where we left off. Those are the two core ideas. And we're going to play with them a lot today. We solved a whole bunch of problems. In fact, this was a nice one. If you had to choose one problem to review from from lecture 1 to make sure you understand both those, I think it's this one. Because here we construct strings that either start with a 0, 1 or end with a 1, 0. And we use both ideas. We say we're going to count number of strings that are 1, 2, 3, 4, 5, 6 digits long. They can either come from set A, which starts with 0, 1, or they can come from set B, which ends with 1, 0. There's some elements that are in both sets, and we can just add those up and subtract off the overcounting. But in order to construct each of these sets, we could use the step rule of counting. Like if you want to figure out how many strings start with 0, 1, you could say, okay, the steps to create a 6-digit string is choose 0, 1, then you have 2 choices for this bit, 2 for this bit, 2 for this bit, 2 for this bit. It's a 5-step process. Step 1, there's only one choice, choose these 2 bits. Step 2, step 3, step 4, step 5. So we can use step processes to construct our strings, but then we can also use the OR rule of counting together in one problem. What a beautiful thing. And at the end of class, we looked at this problem, which we're going to go a little bit deeper into today. Okay. These are the core building blocks, but there's a lot of canonical problems in counting, and these canonical problems show up in probability as well. So it's worth knowing them just because they're a beautiful natural occurrence in our world, but also because they're useful for understanding the topic of today's class. So we talked about this a little bit at the end of class. How many letter orderings are possible of the following string? That is C-H-R-I-S. And the way we thought about this was we can use the step rule of counting. Here's all the orderings. So when we say we're counting number of outcomes, we want to say how many things are on this screen. Each outcome is a distinct construct. We're not doing the task of enumerating all the distinct constructs. We're doing the task of counting how many there are. But the step rule of counting says, what are the steps that you could have used to construct one of these answers? So what are the steps that could be used to end up with curse? Or cur, something like that. And here's steps that we talked about. Step 1, choose your first letter. There's 5 choices for that. After you choose your first letter, there's 4 left for your second letter. No matter what your first choice was, there's always going to be 4 for your second, and then you'll have 3 left over, and 2 left over, and 1 left over. You can have a 5-step process to choose all of your letters. So you can say there's a 5-step process. One of the outcomes could have been choosing H, which leaves 4 outcomes left for the next letters because you could use C, S, I, or R. And you repeat this, and we have a step construction of our outcomes. Because we've been able to break this into steps, and because it has the property that the choice of one step doesn't affect how many outcomes you have in future steps, we can use the step rule of counting. And it's 5 times 4 times 3 times 2 times 1. And in fact, this problem construct comes up so much that it has a special name, and people write down the definition in textbooks, and they call it permutations. Permutations, we're going to consider any ordered arrangement of objects. So if you think of every character as an object, and you think of a string as an ordering of those characters, you can see how unique strings are in fact orderings of objects. If all of your objects are distinct, so all your letters are different, then it's just going to be n, and this isn't like really loud n, this is n factorial, which means n times n minus 1 times n minus 2 going on until 1. And that's the unique number of orderings. So let's warm ourselves up. How many unique 6-digit passcodes are possible on a phone which uses each of 6 distinct numbers? And my story for you is, you're the FBI, you found this phone, and it's got smudges on exactly 6 of the numbers. So you know they're using these 6 numbers for their passcodes, you just don't know what the order is. And how many possible passcodes would you have to try all possible passcodes that uses each of those 6 smudges? Take a moment, say hi to the person next to you, see if you can think about this problem. Okay. Anyone have an idea of how we could approach this? I know that's not enough time, but we got a lot of cool stuff to do today. We have not that many rules we've learned today. We've learned permutations, so guess what? It is?
Just factorial.
It's a permutation, yeah, exactly. It is factorial. And I guess the idea here is, what are the objects that you're ordering? Yeah, the numbers. And are they all distinct? And we want an ordering, so if you have objects, they're all distinct, you want an ordering, you can use the rule of permutations. So the number of distinct orderings of distinct objects is going to be factorial. And there's 1, 2, 3, 4, 5, 6 distinct objects, so it's going to, in fact, be 6 factorial. So 6 times 5 times 4 times 3 times 2 times 1, which is, there's 720 passcodes to check. And I think your iPhone starts to shut down after you've tried like 5. Okay. So there's another question that I think is interesting for illuminating this, how this thought process could be used in a similar problem that's slightly different. What if I said how many unique passcodes are possible if the phone password is some ordered subset of any 6 digits? So now forget the smudges. You just say passcodes have 6 digits in them. How many ways could you make a 6-digit passcode if you say that each of the numbers have to be different? So in this case, there's 6 digits. So there's 10 choices for your first number, 9 choices for your second, if you say that each of the numbers have to be different, 8 choices for your third, 7 choices for your fourth, 6 choices for your fifth, and 5 choices for your last one. And then after this point, you have a step rule that has constructed a 6-digit password where each of your numbers are distinct. And in this case, we don't keep going through the full factorial because our passcodes are only of length 6, not of length 10. If you wanted all the orderings of 10 numbers that are of length 10, it's 10 factorial. But if you want of length 6, at some point you stop and you don't get the full factorial. Instead, you get the factorial divided by all those ones you didn't count. So 4 times 3 times 2 times 1. Okay. So here's my question for you, though. We've talked about how you can order objects if they are distinct. But it turns out this problem gets a lot more interesting if you allow for some of your objects to be indistinct. So for example, if I said, order the numbers 1, 2, 3, 4, 5, we could just use 5 factorial. But the problem breaks down if some of those numbers are indistinguishable from one another. And why is that? In one of your orderings, you'll get 1, 1, 0, 0, 0 in this case. But in a different ordering, you could get 1, 1, 0, 0, 0. Because if you think of these two ones as indistinct, you'll have an ordering where these two ones are flipped, and these don't actually look any different. So if some of your objects are indistinct, there's not 5 times 4 times 3 times 2 times 1 options for orderings. There's something a little bit less. In order to teach you how to derive this, I'd like to tell you a story of Coke cans. And it speaks to a strategy that we use in counting, but we also use in probability a lot. Instead of ordering 1s and 0s, I'm going to be ordering my Coke 1s and my Coke 0s yet again. This is the exact same problem. I'd like to know how many ways are there of ordering these cans, but the Coke 0s are indistinguishable from each other and the Coke 1s are indistinguishable. Making sense? Here's the trick. Here's the pro tip, and you're going to use this pro tip a lot in counting. Even though they're indistinguishable, we're going to make them fancy. We're going to make them be distinguishable just for a moment as a first step in our derivation. So I'm going to take these boring Coke cans, I'm going to name them after all my friends. So I got the Aisha can, I got the Tim can, I got the Irina can, I got the Joey can, I got the Wadi can. And now I took these indistinct objects and I gave them personality. They are now all distinct. And because I've done this, I've kind of brought it into this land of a solution space we understand. So if all your Coke cans are distinct, then solving number of orderings becomes easy again. It's just permutations. If we think about how many ways you can order these distinct cans, 5 options for your first can, 4 options for your second can, you guys are starting to see this pattern, right? So there's 5 factorial ways of ordering them if they're distinct. But now you say, Chris, they're not distinct. And because of that, you've overcounted. There's the time where you have this, the one Coke can that is for Irina, and there's the one Coke can that's for Aisha, and you're thinking about these 2 different orderings as being the same, or as being distinct from each other. So we kind of we've done this simplification, but we have to fix all of our double counting. So I have a task for you guys. I want to count how many Coke cans there are, how many unique orderings there are. I've made all my Coke cans distinct, and I said that there's 5 factorial ways of counting those distinct ones. And I'm telling you I've overcounted. But I have this challenge for you is think how many times I've overcounted. Take a moment, talk to the person next to you. First, see if you can make sure that you both understand the question. And then see if you can figure out a way to figure out how many times I have overcounted by making them all distinct. Talk to the person next to you. Let's see if we can solve this very hard problem together. Okay, let's just try a thought process. If there's 120 different ways of ordering 5 distinct items, but I'm claiming not all of our things are distinct, 3 of the zeros are indistinguishable from one another, and 2 of the ones are indistinguishable, do you guys think the total number is going to be larger or smaller? Just yell it out loud. Yeah, okay, that's good. That's a good smoke test. So it's going to be smaller. We've overcounted in some way. If you've overcounted in some way, there's 2 ways you could have overcounted. You could have overcounted by a fixed number of ways. Like maybe there's 5 of these orderings that somehow break the rule, and you just need to find those 5 and then subtract out the number 5. There's a different way of overcounting. There's a way of overcounting where you have a multiple of overcountings. Like for example, double counting will be for every unique outcome, it's shown up exactly twice in your count of 120. And those are 2 different mechanisms of double counting. It turns out in this case, we've done the second one. So if we think about some of these as indistinct, there's a couple ways that we could think about solving this. And in fact, one of the approaches for understanding this is you could say, I've got my 120 outcomes. Each of those outcomes look like this, where you have an ordering of your ones and zeros, but we think of them as distinct. For every single outcome, you could take the i's and you could switch their places, and you would find exactly one duplicate of that outcome. Does that make sense? So for all the i's, we've double counted. We can take this 120 and we can divide it by 2. But then you'll also find some situations where they'll look the same, but the distinct version will have different subscripts on the zeros. Dividing by 2 solves the problem that the subscripts on the i's might lead to indistinct things looking like distinct, but we haven't solved the zeros. How many ways have we overcounted once we start thinking about the zeros? Does anyone come up with an idea while we were talking? Yes.
So for those 3, you're basically you look at how many ways there are to order those 3 independent of how you've ordered the other 2, and then so that's 3 factorial there.
Yeah, so that's great. Oh, by the way, that was really funny. You didn't raise your hand, but the person next to you was like, that guy knows. Which I really appreciate. So for any ordering of the zeros, you can imagine within our data set, you'll see a version of this string where you see 0 with all these different subscripts in every permutation possible, in every ordering possible. So you'll get WTJ, WJT. All 3 factorial permutations will show up in this format. So it turns out we've also overcounted by the number of ones, or number of zeros that are indistinct, that we treat as distinct, all the different orderings of those. So in fact, this should be 120 divided by 2 times 3 factorial. There's a second way you could get this insight. And this is a little bit nuanced, but this shows the derivation for the rule we just used. So if you want to get away from intuition, you just want cold, hard math rules, this is a way you could have derived it. You could have said, I want to think of this 2-step process that creates all the permutations of distinct objects. Let me give you a 2-step operation that will lead to permutations of distinct objects. Your first step is make all the permutations where some of your objects are indistinct. So all the permutations of zeros where zeros are indistinct, and all the permutations of 1 where 1s are indistinct. This is the target we're looking for. That's the thing we're trying to count. But that's the first step in this 2-step process. First, you make those, and then as your second step, you find a way to switch out the zeros and 1s. You choose some ordering for the actual subscripts. the I's and the A's, and then after you chose the orderings for the subscripts, you choose the orderings for the subscripts of the second indistinct group. So this is a two-step process that describes how you can get all the permutations of distinct objects. We're not trying to calculate the permutations of distinct objects. We're trying to calculate how many things are in this step. But those of you guys who are fans of multiplication division know that, like, oh, I can just get you cheekily over there. And then you have a way to calculate the permutations where some of your objects are indistinct. That's the situation we have. You know, some of the zeros are indistinct and the ones are indistinct. Is you just count how many permutations there are, imagining they're all distinct, and then you have to divide out how many ways you could permute each of the groups of indistinct objects. So again, that would lead to 120, so that's 5 factorial divided by 2 factorial times 3 factorial. I forgot a factorial here. Is that a problem? Like, that derivation suggests that this should have been 2 factorial. Did I make a mistake? Thank God. And it's because 2 factorial is in fact equal to 2, because 2 times 1 is just 2. Okay. This leads to a general rule. So the general rule is, let's say we want to count orderings of objects, and not all the objects are distinct. You have different subcategories of indistinguishable objects. Like n1 of your objects are the same, n2 are the same in a different way, and nr are the same in an rth way. The rule is the total number of permutations are n factorial divided by n1 factorial times n2 factorial up to nr factorial. Okay. Last class, I gave you guys this teaser at the end of class. I said, how many different orderings are there of the word Mississippi? You now have the rule. Confirm it with the person next to you. Make sure you understood this very important rule in counting. How many orderings are there of the letters MISS, ISS, IPPI? Go for it. Okay. You know, there's an art form to mathematics. Especially as you get into higher level mathematics, like, where do you go from CS109? Like, what's the next step in your mathematical journey? You'll learn a few more classes, but you're getting closer to the forefront of, you know, what humans know. And if you take math beyond that forefront, so much of it is creativity. So much of it is taking the real world, finding mathematical constructs, and either recognizing that they're already solved problems or realizing that you've discovered an unsolved mathematical problem that you can work on. So there's this art form in mathematics of somebody gives you a construct like this and you have to formalize it. And that's very similar to what my day-to-day life looks like when I'm doing research in math. It's hard though. I mean, in this case, maybe we only have a few tools, but as you add more and more tools, it can be a hard task. And that's one of your learning goals in CS109. Not just knowing the formulas, but knowing how you can see the mathematical structure in the natural world. Okay, so you're like, what's natural about the string Mississippi? Well, you know, we're at the beginning of CS109. It gets more and more natural. Mississippi, how many letters are there? I actually don't know, but I think it's like 11. Okay, woohoo! So how many orderings are those letters? There's 11 factorial. Am I right?
Yes.
No, so very distinct. Sorry, I guess that was really cheeky of me. Yes, there are in fact 11 factorial orderings of the letters. But if you did 11 factorial, it would give you every ordering, and it's thinking about these s's as being different from one another. So you'll get an ordering where like these two s's are in the different order, and that doesn't actually look like a different word. I've overcounted. How many times have I overcounted? Someone help me out here. 4. Wait, where did 4 come? That is magical. Where did this come from? Oh, there's 4 s's. And all the s's look indistinct. So I've overcounted because for every true unique ordering, you'll get every permutation of those indistinct s's. Okay, great. What else have I overcounted? Am I done? Okay, there are, you get the 4 i's. Okay, 4 i's, and then how many m's are there? Is it going to mess it up if I put in 1 factorial here? No, divide by 1 doesn't matter at all. But you know what? I feel like including you, M. Welcome to the party. Okay, who else gets included in the party? Oh, and do I just do p factorial here? Silly. I think there's 2 p's. Yeah, feeling good. And have I gotten them all? Okay, there you go. Now you can know how you can do orderings of Mississippi. Is this important to know how many orderings are there were in Mississippi? Yes. No, I'm just joking. But is the mechanism of how he derived it important because it applies to lots of problems in further mathematics? Absolutely. Permutations, especially of indistinct objects, show up a lot in fundamental theories, but it's, fun party fact. Okay, so in this case, 11 factorial divided by 4 factorial, 4 factorial, 2 factorial, there's 34,000 different orderings of those letters. Okay. Now, I do want to show you, because you're computer scientists, one of the things that you can do as a computer scientist if you're finding any of this stuff hard. You have the power of computers. We're talking about counting how many outcomes there are. So if we say we want all the orderings of the words boba, we want to know how many of those are. We don't have to construct each one, but as a computer scientist, one of your ways to solve this would be to write some code that constructs every single ordering. And Python has a beautiful tool called permutations. And if you call permutations on any list, it will construct every permutation of the elements in that list. In this case, I put that through a set, and then I just print out everything in the set. I do some pretty printing. This is a little bit of advanced Python. Except for this line, and maybe the fact that this function exists. If some of this code is looking novel to you, come to Friday's review session. We're going to talk all about Python. It's a beautiful thing, but it's also the language of pseudocode. So if you don't know Python, hopefully this is making sense. Take my letters, get every single permutation, and then print them out. So you can use the power of Python to help you out. This would be a really, really long way of finding out that there are 4 factorial divided by 2 ways of solving this. Here's the shorter way of counting how many outcomes there are. You can say, Python, what's 4 factorial? Python, what's 2 factorial? Python's like, it's 2, but Python's so polite. It's never condescending. It'll just give you back 2 very politely. And then you'll get 4 factorial divided by 2, and you get the answer much quicker. Okay. So now you know a little bit of code. Here are all the formalizations of tasks we're going to do. So what we've just talked about is how you can sort objects. And you guys have become really good at counting orderings of objects. And you might feel like, is that the only task counting people care about? No, we care about other things, like objects, or choosing objects and putting things in buckets. You're like, do you care about other things like your family? It's like, no, I just care about these 3 tasks. No, I'm kidding. Let's talk about some other tasks. And actually, though, I do want to give us one more challenge, because even though we're going to talk about canonical tasks, I want you to always return to those 2 rules we learned last class, the step rule of counting and the OR rule of counting, because those are your building blocks. It's easy to take a problem that's slightly different from a permutation problem, where you have to combine those building blocks with canonical things like permutations. Let me give you an example. We're going to go back to our trusty old phone, and now instead of having 6 smudges, there are 5 smudges. It is still a length 6 password. So my question for you is, if there's 5 smudges, how many unique passwords could exist? And this is just an example of why you want to know those fundamental rules in addition to the generalized formulas like permutations. You guys want to get to know that person next to you? This is a little challenging, but think about it, and it's certainly solvable with the tools you have. 5 smudges, 6-digit passcodes. How could we possibly do this? Okay, let's get amongst. Okay. I often ask you some pretty hard questions in lecture. This is a pretty hard one. What I'm going to do in lectures, I'm going to show you lots of examples, and that way you'll get some intuitions. When I look at a math problem, I'm not starting from scratch. I have seen many, many math problems solved. They live somewhere in my brain, so when I see a new problem, I kind of do some sort of pattern matching. I do think about the problems I've seen before. So in lecture, I'm going to show you lots of examples. I'll ask you to solve them like you're seeing it for the very first time, and that's hard. All I ask of you is that you engage with it. You get your mind amongst it. Because if you get your mind amongst it, even if you don't derive this really hard problem on the spot, when you do see the derivation, you'll be a little bit more ready for it, because you'll at least appreciate the difficulties. So whether or not you got the answer, let's talk about it together. I also have a pro tip for you guys. Let's say you're working on a problem set starting today. When you're working on the problem set, there'll be a lot of counting problems. And sometimes you'll look at a counting problem like this one, and it will look daunting. A first step, if you find anything hard, is to start writing examples of outcomes you're counting. Like, it's really abstract what we're counting here, but if I make concrete outcomes, it becomes a little clearer. Okay, I'm counting all of these different outcomes. You know what your outcomes look like. One of the reasons that's also helpful is if you use the step rule of counting, you're explaining steps that could generate each of your outcomes. So, speaking of which, what are steps that could generate each of these outcomes? Okay, an idea.
Choose the 5 numbers, and then choose which, you know that you need to use all 5 because of the smudges, so exactly 1 must be repeated. So you choose which one you repeat, then you choose the 2 slots in the sequence where you use that repeated number, and then you permute the rest of them.
Okay, that's a very good way of thinking about it. Step 1. We know there's exactly 1 digit that will be repeated. Your first step is to choose that digit to repeat. How many choices do you have? You could choose to repeat the 2, you could choose to repeat the 4, the 5, the 6, or the 8. All those are good choices for the digit that gets repeated. That's our first step. Does that construct an outcome? No, it just chooses a digit. We need to continue our construction ways. Your step 2 is to generate the passcode. You now have 4 distinct objects and 2 indistinct objects. You know, there's 1 number which is repeated, and there's 4 numbers that occur exactly once. So if you have 6 objects, 4 of them are distinct, and 2 of them look indistinct, how many ways could you order those 6 objects? Yeah, just say it out loud. What are you thinking? Hey, yeah, louder, much louder. It's okay if you talk over each other, it's fine. Okay, but I really appreciate that you guys don't want to talk over each other. 6 factorial. But 6 factorial overcounts the fact that 2 of them are indistinct, and you need to divide by that 2 factorial, just like we were doing over here. So there's 6 factorial ways of ordering your digits, divide by 2 factorial to deal with the overcounting. So there's 5 choices for the double digit, and then your next step is to take those things that you've set out on your table and actually come up with an ordering, and there's 6 factorial, divide by 2 factorial. So this combines a rule we just learned into the step rule of counting. So we're going to show you these canonical rules, but always remember your 2 most fundamental ones, the step rule of counting and the OR rule of counting. Okay, so at this point, you guys are old enough and you guys are wise enough to learn about combinations. Combination is a different counting task. In this different counting task, we're going to take objects and we're going to choose some subset of them. So, you know, my example that we're going to run with is eventually going to be, I have 5 books here. I want to figure out how many ways could I choose 3 of them. And you can start thinking about that. But I'm going to tell you guys a story. I'm going to tell you guys a story, and it's going to show us how we can solve all the problems in this space. And it involves cake, a delicious thing. In fact, actually, I have a 1.5-year-old, right? She discovered cake like 2 weeks ago. And it's like deep in our psyche. She like had that, and she's like, that is good stuff. And like ever since she's like, how about more cake? And we're like, what if we ate dinner? And she's like, no, more cake. So going on that vibe, let's learn about counting of combinations using cake. We're going to have a party. And in this party, there's going to be 20 people. But this isn't a very nice party. We're only going to give 5 people cake. You're like, what sort of awful, like diabolical human being are you? Ha 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 ha. So this is the task of choosing a subset. So you have 20 people, we're going to choose a subset of 5 to give cake. Can I tell you a story of how we could come up with every different way we could give 5 people cake? We could say, here is a generative story. And generative story is invoking the step rule of counting. I'm going to show you steps that could lead to an outcome where we've given exactly 5 people cake. We get all the people in our party in a line. Also not a good thing to do at a party. Then after that, we're going to say, hey, everybody in this line has an ordering. They have a location in the line. And we're going to take those first 5 people, and we're going to give them cake. You're like, you awful, awful person. Give everyone cake. So we got n people in the line. How many ways could we do that? Well, it depends if people are distinct. Are people distinct? Yes, of course. No 2 people are alike. We are all individuals. We all have our own hopes and wants and dreams in this wild world. We're all distinct. So it's permutations of distinct objects. There's n factorial of them. Step 2, there's only one way of doing step 2, and it's to draw a line after the first person. And it's going to say, every person in the front of this line, welcome to the cake room. And there's only one way of doing this, this next step. But now that we've put all these people in the cake room, we're going to give them cake. But if you think about an outcome where these 5 people get cake, it doesn't really matter which order they're standing in. They all get cake. And so they could be this way in the room. They could be a different permutation in the room. Any permutation still leads to exactly those 5 distinct people getting cake. So you imagine the next step is I'm going to let all these people in the room chill and intermingle and enjoy their cake. And so they can go spread out, and we're going to say they can, when they intermingle, there's going to be 5 factorial ways that they could intermingle within this group. So if my next step is to let them intermingle, there's 5 factorial ways of doing that next step. Now, all these other people who are not in the cake room, they've also not gotten cake. But in this construction, I've chosen these 5 people to get cake. I've chosen these 15 people not to get cake. But I'll have an outcome for every ordering of these 15 people, even though in that outcome, this exact set of 15 people didn't get cake. I've overcounted by 15 factorial. In my last step, I have to let these people who are not in the cake room, I have to let them intermingle. Now, if n is the total number of people and k is the number of people who got cake, there's n minus k factorial ways that I could let these people intermingle. And then you're like, I'm not an awful person, so I'm like, just kidding, you guys all get cake, and then I bring cake to everybody, and then we have a party. And we're like, why are we in different rooms? We should all be in the same room having this blast of a party. And everyone's like, yeah, cake, no dinner for us, we're adults, we get to make our own choices. What have I done here? I've given fake people cake, but in the process of this story, I wanted to give you a deep idea for where the rule comes from for counting ways that you could give k, or you could choose k, a subset of size k from a group of size n. Formally, outside of the world of k, we call this a combination. So if you have k objects, you want to choose a subset of n, we're going to call that a combination. And the rule for a combination is the number of ways that you could do that. The ways you could take your 20 people and choose 5 to get cake would be 20 factorial. But then you have to divide out the 5 people in the room with cake, and you have to divide out the 15 people in the room without cake. Because if you think about this as an ordering of that line of people, not every of those ordering is a distinct assignment of cake to people. So we've counted by this many times. And the derivation was, n factorial ways to line people up, 1 way to put the cake, not cake split. There's k factorial people in the cake room. They need to not worry about ordering. And there's n minus k people who are not in the cake group. We also need to not worry about ordering. So we can have this 1, 2, 3, 4-step process that could generate a particular assignment of chosen cake people out of your set of n. You should know that derivation because it's fun and interesting, and I think it's illuminating, and it can teach us things about probability. But you can also just know this general canonical process. If you want to choose a subset of size k from a group of n, you can just use this equation. Now, this equation shows up so much in so many distinct parts of mathematics that it gets its own notation. You might see this. It's called the binomial coefficient. Nothing we've talked about has anything to do with binomial distribution, but it turns out the coefficients, if you had to set up a binomial equation, end up having weights that can be derived using this formula as well. There's lots of parts of mathematics where this exact calculation shows up. So we have this special notation for it, and if you see a problem and you can understand it as choosing a subset, you can just use this equation. Quick check. In this problem formulation, are all your objects assumed to be distinct or indistinct? Distinct. Think about your people. They're all different, unique individuals. If you want to choose 3 items from a set of 10 and they're all indistinct, how many ways are there of doing that? Yeah, because if they're all indistinct, it's like you have 10 Coke cans, you choose 3. I have 3 Coke cans. And no matter how you choose 3 Coke cans, it looks exactly like 3 Coke cans. There's only one unique outcome. So if everything is indistinct, this problem is actually not that interesting. So we are marching right along. Now, I told you, as a motivating example of this, not to think about cake, but to think about a slightly more realistic problem. Say I have these 5 lovely textbooks. I have the course textbook. Do you know the course has a textbook? It's a really good resource if you want to go even deeper into some of this stuff. Humans in New York, they tell stories, most of the humans, mostly in New York. The definition of everything in mathematics, quite a small book. I like this book. It's called The Theory That Would Not Die. It's about Bayes' theorem and how Bayes' theorem allowed Turing to break the enigma in World War II, how it kept showing up in the 90s in the revolution of mathematics that came from the computer science departments, and how it continues to influence thinkers. In fact, a few of the papers I've written in new algorithms have in fact used this old idea called Bayes' theorem. Where could you learn about Bayes' theorem? In this class, you're going to learn about it in this class, like in a couple weeks. How cool is that? And this is really cute. One student took the course reader and published it into like a hard book, which is like kind of a funny thing. There's only one copy in the world, so I'll fight you to the death over it. Or maybe I'd lend it to you. Let's say there's 6 distinct books and I want to choose 3. How many ways could I do that? And to be clear, if I give you these 3 books, do you care if I give it to you like this, or like this, or like this? No, it's the same 3 books. You just care that I gave you these 3 books as opposed to these 3 books. So in this problem type, we don't care about ordering. We just care about what was chosen. So there's a combination choosing 3 books out of 6. Take a moment, and instead of talking to the person next to you, think about it. You're like, do we have a rule for this? Like, yeah. You don't have to go to the Kate derivation. You could be like, okay, I'm going to get all my books in a line. I'm going to draw a cutoff at 3. Then I'm going to let these go into a room and permute. I'm going to get these remaining 2 to go into another room and permute. And then I have 5 factorial divided by 3 factorial divided by 2 factorial. You don't have to go to that origin story. You could, good times. Or you could just say, I recognize this as a combination problem. All my items are distinct. And I'm choosing a set of 3 from a set of 6. So there's in fact just 6 choose 3 ways. So you can say this is 6 choose 3, which is the same as 6 factorial divided by 3 factorial divided by 3 factorial. 20 ways. OK. So here's another instance of this problem. And this is going to be a subproblem and something you'll see in your problem set. So worth paying attention to. I have myself here a deck of cards. It is a standard deck of cards, except that they're awesomely large. A lot of games involve getting a hand of 5 cards. And in this hand of 5 cards, it does not matter the size of the cards. It does not matter the ordering of the cards, but it does matter which of the cards you get. All the cards in a deck of cards are unique, if you didn't know. They all have a unique combination of number and suit. And so this is different from, say, this hand. And if you want to do mathematics around gambling, and much of probability was invented by people who were horribly addicted to gambling, and they were inventing probability so that they could beat their friends, you would have to be able to count how many different hands of cards are possible. So you have a deck of 52 cards. How many ways could you get, say, 5 cards? And at this point, you're like, I know this. I'm starting to get comfortable with combination things. I'm starting to see this in many problems in the world. This is, in fact, a combination. Now, if you wanted to calculate that combination, you can just say, in Python, you can ask the question, hey, what is 52 factorial divided by 5 factorial divided by 52 minus 5 factorial? Let me go to the code for a second. And I have myself here a video server, the problem set app, and over here is a way to count how many unique hands there are in cards. So check out this Python. I'm going to first do this the long way, and then I'm going to do this the short way. In the long way, I'm going to construct a deck of cards with 52 different cards. I'm going to take, for every value and for every suit, I'm going to get every combination. Afterwards, there'll be 52 elements in my list of cards. These 4 lines just create a deck of cards. I told you that Python has this thing called iter tools. You can also say, give me every combination. If I say iter tools, give me every single combination, it will give me every combination of the cards of size 5. And it'll give it to me as a list, and I can print out the length of this list. Let's just run that, because what a good time. Count hands. And it says there are 2.6 million unique choices of 5 cards from all your 52 cards. If you wanted to, as a computer scientist, you could actually look at what each of those are. So for hand in subsets, you could print out each hand one at a time. And if I do this, every single line here will show up exactly once. It'll be one unique choice of cards. How many times is this program going to run? Or how many lines is it going to print out? 2.5 million, that's too long. I am not patient for that. So I want to use this as a chance to enumerate the difference between we're counting versus we're going to generate each of the outcomes. In this part of CS109, we are just counting how many things you have to do. Instead of creating all of these cards, though, we could have just done this. We could say, you know how many hands there are? We can do, either you can ask Python, what is 52 choose 5? And it will, hey, did I not save? I always forget to save. We've all been there. And it'll say 2.5 million. Or similarly, I could say, hey, the formula for 52 choose 5 is math factorial of 52 divided by math.factorial of 5 times math.factorial of 52 minus 5. And you guys are getting way of people reading. Can you guys see that? Math factorial of 52 divided by math factorial of 5 times math factorial of 52 minus 5. All these three things get you to the same answer. The factorial gives you a way to count the number of outcomes in a much faster way than if you had to generate every single outcome yourself. And also, I just wanted an excuse to show you guys some cool code. So now you know, as computer scientists, you can do this like even cooler than the math friends that you've got. Yeah. One.
I guess my question is this basically not what we did before? Like we're treating the people in the cake room and outside the cake room as indistinct. So it's the same thing, like if we take factoring the entire thing divided by treating like the 5 people inside the room as interchangeable and all the people outside.
You've done a beautiful thing. It's not very obvious, but what you've seen is you've recognized that this combination is very similar to ordering of indistinct items. You have two groups of indistinct items, people in cake room and people in not cake room. For some of you guys, this is like totally going to be a mind flip. Once you've seen a problem one way, it's sometimes very hard to see a different way. But you're absolutely right. There is an equivalence between those two problems, and you've seen it. If you don't see it, that's absolutely fine. But if you guys want to think about it a little bit more, that's a really cool thing. Can you recognize why does this formula look so similar to ordering of items where some of your items are indistinct? And if you can flip a problem, there's always an equivalence where you can do a combination and express it as an ordering of distinct and indistinct. I don't think that was your question. You had a different question.
It was not. That was a very cool question.
Yeah.
My question is, just kind of fundamentally, why do we really care about, like, for example, the cake room, the 15 people who are not part of the cake room? Why do we care about that permutation?
You're sorry. Like, we shouldn't care about them if we're just choosing people for cake. But if you don't count them, we know we'll get a different answer than we got from itertool. So clearly, it's an important step in getting the right answer. But what's going on there? If you just construct your cake room, let's choose a smaller number. By the way, other pro tip, if something is hard and you want to think about, choose small numbers. Let's say there's 6 people and we're going to choose 3. That's the book example. So we put 3 people in our cake room and 3 people in our not cake room. If step 1 is to come up with all orderings, there's 6 factorial different orderings. And in some of those orderings, you'll get these 3 people here. And you've figured out a way to come up with every overcounting of those people inside. But if you took any single one of those, where you had like this person, this person, this person, when you generated your 6 factorial, you'll get every permutation of people outside. You'll get like x1, x2, x3. And you'll get x2, x3, x1. So when you start with 6 factorial, that describes the size of a huge set. And within that set, there is groups where even if you thought of these as indistinct, you've already handled that case, you will see an outcome which is these 3 indistinct things get cake, and these guys don't get cake. And then you'll have this outcome which looks basically the same, but you just have treated these people outside as indistinct. It's a really cool, subtle question. But you do need to deal with the fact that in our first step, when we created all these 6 factorials, we generated a lot of examples of different orderings of people not getting cake. Very subtle, very cool question. OK? Whew. let's take our 2-minute pedagogical pause. Before we do that, what can you do during your 2-minute pedagogical pause? You can have a good time, you can talk to the person next to you, but if you want to, the number one thing you could do for learning is to try and crystallize what we've learned. Try and summarize what we've done so far before we move into the next great topic of CS109. Okay, fantastic. Take your 2-minute pedagogical pause. Talk to you in a second. Okay. We have one last thing to do today. But I wanted to celebrate. We did something, kind of straightforward. We made it more complicated. This thing had a whole cake story. That was wild. And we're getting into the final task that you need to do in counting in CS109, and that is, let's figure out how we can put some stuff in buckets. Let's do it. We're going to be thinking about distinct case, and then we'll think about the indistinct case. Thinking about the distinct case, imagine you have 4 distinct things and you want to put them into 3 distinct buckets. It turns out that this is a little bit straightforward using the step rule of counting. Each distinct thing chooses its bucket. First distinct thing chooses its buckets. Its number of buckets options. The next distinct thing chooses its bucket, number of buckets. Because each of your objects are distinct and each of your buckets are distinct, it ends up just being you have all the bucket choices for the first string. This is putting strings into buckets. All the bucket choices for your second string, and all the bucket choices for your nth string. You could have derived this from first principle. In fact, if you never memorized this rule, even if it was like an exam setting, this is the sort of thing that if you knew your step rule of counting, you could come up with. But if you have distinct objects being put into distinct buckets, it's just a power. So maybe sit with that for a second. See if you can think of a good question. Is there anything confusing about this? It's R times R times R n times. There's n steps, and each step has R options. What's R? The number of distinct buckets we have. And what's n? The number of distinct items. So choice of buckets times choice of buckets times choice of buckets n times. Okay. It's going to get a little bit more exciting, though, when we think about indistinct things into our buckets. You guys ready for it? Okay, I'm going to close my slides for a second, and we are going to just think about this using physical objects. Oh, that's kind of interesting. It's stuck on that slide. Good times. I have myself here 4 indistinct objects, and I would like to put them into buckets. May I tell you another story? Because if these were distinct objects, which they are not, and we wanted to put them into buckets, and we think of each of our buckets as different, that's not too bad, because there would be number of buckets choices for this little fellow, number of buckets choices for this little fellow, number of buckets choices for this little fellow, and number of buckets of choices for this little fellow. And that would just be buckets times buckets times buckets, buckets, buckets to the power of 4. But they are not indistinct. Or sorry, they're not distinct. They all look the same. So if you use that formulation, you will have overcounted. I told you there's 2 different ways of overcounting. Sometimes you overcount by a fixed number, you subtract it off. Sometimes you overcount by a multiplicative, you divide it out. Unfortunately, if you went about starting with this formulation, thinking of them as distinct, and then try and subtract or divide out, your mind will explode. Instead, there is the most wonderful, creative, interesting description for how you could derive how many ways you could put those things into buckets. I am going to introduce you to my new friends, the dividers. We're going to put those cans into, well, let's say 3 distinct buckets. If I want to put those cans into 3 distinct buckets, I'm going to introduce 2 new friends, divider 1 and divider 2. And what I'm going to now do is I'm going to think about ordering not just my Coke cans, but my Coke cans and these 2 new friends are dividers. So here's one ordering of my Coke cans and these 2 dividers. Notice that ordering is a thing we already know how to do. If I ordered my Coke cans and my dividers like this, I can interpret it as this Coke can is in this bucket, these 2 Coke cans are in this bucket. Sometimes your dividers just fall off, and that doesn't really get my dividers are going to be face down, because then no one gets hurt. So I have my face down dividers. It's okay, it's like $10,000 worth of equipment. But this tells you that there's this, one Coke can in this bucket, and then whatever between these two dividers I think of in bucket 2. And in this case, I've got 3 buckets. My claim is I can think about any assignment of my indistinct objects into buckets by thinking about an ordering of both the Coke cans and the dividers. So if you gave me any ordering, like this ordering, for example, or this ordering, for example, like there's just not enough space for you guys, Coke cans. You're up here. You can't see it? Okay. Here you go. I have 2. Can you see it now? Okay. If I have 2 dividers and Coke cans, any ordering of these 6 objects you give me, I can interpret as Coke cans and buckets. This is how many things are in buckets in the first bucket. How many are there? This is how many things are in the second bucket. How many are there? 4. This is how many things are in the third bucket. How many are there? 0. Oh, you guys are good. What if I did this? How many in the first bucket? 2. How many in the second bucket? 2. How many in the third bucket? 2. Oh, you guys are good. Any ordering of my Coke cans and in my dividers leads to a unique assignment of Coke cans into buckets. But now we have a challenge. How many orderings are there? I have 4 Coke cans. I have 2 dividers. I have 6 objects. Are there 6 factorial different orderings? I see some shaking of heads. You guys know that doesn't count because 4 of my Coke cans are indistinct. And this is orderings with some indistinct items. How about those dividers? If you have 2 dividers like this and 2 dividers like this, we still think of this as bucket 0. We still think of this as bucket 1, and we still think of this as bucket 2. So if you just switch the ordering of the dividers, it doesn't change which Coke cans go into bucket 0, 1, or 2. So you can think about all the orderings of your Coke cans, and you can think about all the orderings of your dividers. And this is how many times we've overcounted. So if there's 6 factorial divided by 4 factorial divided by 2 factorial, that is the number of ways that you could put 4 objects into 3 different buckets. Do you notice how the number 3 didn't show up there? And it's not because it didn't show up there. It in fact did. It showed up because there's not 3 dividers, there's 2 dividers. Why would there be 2 dividers if there's 3 buckets? It's a fence post bug. If you have 6 buckets, you've got 5 dividers. If you've got 3 buckets, you've got 2 dividers because there's a bucket on one side and there's a bucket on another side. If you want to see this problem using helmets instead of Coke cans, you absolutely can. But no matter how you derive it, there is this simple rule for how you can count ways you can put stuff into buckets if some of your stuff is indistinct. You think of your n indistinct items, and you think of your r-1 dividers, and we're going to get all the orderings of those. But then we're going to divide out the fact that in those orderings we thought of your n items as distinct, but they're not. And then we're going to divide out the fact that in this ordering we treat the dividers like they're distinct, but they're not. And if you do this, you end up with n plus r-1 factorial divided by n factorial divided by r-1 factorial, which gives you the rules for how many ways you can put indistinct items into buckets. And there you have it. It's a formula that you can use. And the derivation would be a really hard one to do, but you could figure it out if you wanted. We're going to come back on Friday, and we're going to talk about probability. And to do probability, you need to know this one very well. You need to know this one very well. And you need to know this one very well. All the versions of indistinct. If you like this, go do problem sets and do problems 1, 2, 3, 4 before Friday. If you really like this, this is the coolest example I've ever written about counting. Go check it out. And if you really like this, here's a challenge problem you can think about between now and Friday. Have a great day. See you next Friday.